Hey guys, this video is about equilibrium and the equilibrium constant K. So many chemical reactions, particularly those that occur in solution, aqueous solutions, um, are at an equilibrium, what we call dynamic equilibrium. And so the idea is this. So let's start with our generic chemical equation. Remember the lowercase letters stand for the coefficients and the capital letters stand for the species. So generic equation, AA plus BB, CC plus DD. Now the double arrows mean equilibrium. And what that means is that when the reactants come together to form the product. So in this simple reaction, there's only one product, so maybe D would be 0. But so they're over here, they're separate, and they're combining and they're forming these products. Now, if we take a container and we put these reactants in there by themselves, at first what happens is they start coming together and forming the products. But once we start forming more and more of these products, what will happen is that every now and then at first, these will start to go back over here and break apart. Like that. And then more will come back over here and form some products. And at first, we have more reactants going this way, making products, than we do products going back to form the reactants. But equilibrium is the point at which the rate of the forward reaction is equal to the rate of the reverse reaction. So if we look at this graph down here, this is graphing the reaction rates, how fast these reactions this reaction is occurring versus time. So at time equals 0, we aren't making the product, we don't have any products, so they're not going back and making any of the reactants. We just have the reactants starting to make the products. Now, as we decrease the amount of the reactants present, the rate decreases, and the rate of the products reforming the reactants starts increasing until we reach this point right here. At this time, the rate, remember this is the rate, how fast that's happening, of the reverse reaction is equal to the rate of the forward reaction. Once we reach that point, we are at equilibrium. And so if we could reach down inside of that container and we could see the individual atoms and molecules, what we would see is some of them coming together, forming the products, and some of them breaking apart and forming the reactants, reforming the reactants. And so they're constantly going back and forth. This is a dynamic process. But taking a step back out and looking at it from the macroscopic point of view, it looks like everything's steady because the concentration, the amount of everything is staying the same, even though down there at the atomic and molecular level, things are moving back and forth all the time. So that's dynamic equilibrium. For example, the reaction of nitrogen and hydrogen to make ammonia, all gases here. So this might represent what the equilibrium would look like. So maybe the white ones would be hydrogens and the orange ones would be the nitrogens. And so at first, when we first put the nitrogen and hydrogen in there, the concentration, now this graph's a little different. This is the concentration, not the rate, versus time. And these are the three separate species. So hydrogen and nitrogen are the two reactants and ammonia is the product. So at first, we have some hydrogen and we have some nitrogen, but we don't have any ammonia. As the nitrogen and hydrogen start combining to form ammonia, the concentration of ammonia starts increasing, and the concentrations of hydrogen and nitrogen start decreasing until at equilibrium, their concentrations stay the same. So at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction, but also at equilibrium, the concentrations are constant. Even though individual atoms and molecules are moving back and forth, the concentration from the macroscopic point of view stays constant, stays the same. And so we can say by looking at this equation, this equilibrium reaction, that, for example, for every 1 mole of nitrogen that reacts, we form 2 moles of ammonia. For every 1 mole of nitrogen that reacts, we need 3 moles of hydrogen. We could also talk about that in terms of, say, concentrations. For every 1 mole per liter of nitrogen that reacts, we need 3 moles per liter of hydrogen, etc. Or we could say, for example, for every 2 moles per liter of ammonia that form, we need to react 3 moles per liter of hydrogen. So now the equilibrium constant, K, and the law of mass action. So it ends up that at equilibrium, the ratio of the reactants over the products, each raised to the power of their coefficients, is a constant. Now, so here's our generic equation, AA plus BB in equilibrium with CC and DD. So this is important for you guys right here. This is really at the heart of all the equilibrium calculations we're going to do. We're basically using this, the equilibrium expression, which is what this is. K equals products of reactants, each raised to the power of their coefficients. And basically we do a bunch of algebra. So again, these are the products, C and D. So remember, the capital letters stand for the formulas, and the lowercase letters are the coefficients. So the coefficients become the exponents. Right? For example, in our example reaction, ammonia being formed from nitrogen and hydrogen, the equilibrium expression would look like this. K, the equilibrium constant, is equal to the concentration of ammonia squared, because its coefficient is 2, divided by the concentration of nitrogen, coefficient of 1, so it's exponents 1, times the concentration of hydrogen to the 3rd power. We are not going to use units for the equilibrium expressions, equilibrium constants. It's possible, but it's not. This is the one time where it's not worth using units, in my opinion. So we're just going to kind of trust that units work out. And they will. They do. So here's an example. So we start out with that same reaction. So this is the same equilibrium reaction we're talking about. We start out with 0.35 moles of nitrogen and 0.95 moles of hydrogen. So that's before anything happens. That's before any of the reaction happens at all, in a 1.8 liter container. And now we allow it to come to equilibrium. So the nitrogen and hydrogen start reacting, start forming ammonia, and then the ammonia starts breaking apart, reforming nitrogen and hydrogen until we get to equilibrium. At equilibrium, so now we're not in the beginning of the reaction anymore. We're at equilibrium. We have 0.47 moles of ammonia. What's the value of the equilibrium constant K for this reaction under these conditions? So I'm going to let you guys work this out real quick and come back when you get an answer. But remember, these are initial concentrations here. This is equilibrium concentration here. That's different and it matters. Plus, actually, these aren't concentrations. These are moles. In order to write down an equilibrium expression, at this point we need the concentrations, which is the moles over the liters. All right, so go ahead and work that out and come on back when you're done. Welcome back, guys. So I'm going to start out by calculating the concentrations, the molarity, the initial concentrations of everything, right, in our container. So nitrogen, the initial concentration be this 0.35 moles over 1.8 liters is 0.19 moles per liter. Hydrogen, get about 0.5253 moles per liter. And initially we have 0 ammonia, so its concentration is 0 moles per liter. Now, what's going to happen is, as this reaction starts happening, it starts unwinding, the change, if we look at this equation here, and we say, if we call the amount of nitrogen, the number of moles of nitrogen, or the concentration of nitrogen that forms, that is used to form the ammonia, call that X. Because we're losing it, the change is going to be minus X moles per liter. And because for every 1 nitrogen that reacts, 3 hydrogens react, the change in concentration of hydrogen is going to be minus 3X. And then because we make 2 moles per liter of ammonia for every 1 mole per liter of nitrogen, the change for ammonia is going to be plus 2X. These signs are important. So that means, right, at equilibrium, once everything's settled down and the rate of the forward reaction is equal to the rate of the reverse reaction and all the concentrations are constant, then at equilibrium, the concentration of nitrogen will be its initial concentration minus X. The concentration of hydrogen will be its initial concentration, right here, minus 3X. And the concentration of ammonia will be 2X. But here's the thing. To do this problem, we're told at equilibrium how many moles of ammonia we have, 0.47. So if we calculate the concentration of ammonia, 0.47 moles over 1.8 liters, you get 0.26 moles per liter. And remember, that's equal to 2x. So x, see, if we get x, we can get everything here. So we solve this for x by dividing by 2, and we get this. The reason that's nice is because if we look at the equilibrium expression down here for this reaction, which we've already seen, it's ammonia squared over nitrogen times hydrogen cubed concentrations. If we know the equilibrium, and it's important that these are the equilibrium concentrations of everything, we can just plug the numbers in here and we'll get our k, the value of k. Well, that's what this up here is doing for us. Once we get x, we can come back and plug in here. That's what's happening here. And we get the concentration of nitrogen at equilibrium, concentration of ammonia at equilibrium minus 3x. Get that. And then concentration of ammonia at equilibrium is 2x. And so we plug these numbers in here, and we get k is equal to about 400. The 1 sig fig, by the way, came from this right here. When we did this subtraction, we're only allowed to keep, because x is 2 past the decimal, this is 2 past the decimal, we can only keep 2 past the decimal, which ends up being only 1 sig fig. So k is 400. All right, so we can manipulate the equilibrium constant, or rather, I should say, the equilibrium constant k changes when we manipulate the equations. And here's the two things we can do. If we reverse a chemical equation, an equilibrium reaction, if we write it in the reverse direction, so instead of AA plus BB going to CC plus DD, we write CC plus DD in equilibrium with AA and BB. The equilibrium constant for this new equation is the inverse of the original. So if this is K prime, we just use prime to distinguish the different K's. It's just going to be equal to the products A, B over reactants C and D, which is just 1 over this. So when we reverse an equilibrium reaction, we invert the K, 1 over the original K. The other thing we can do, guys, is we can multiply all of the coefficients through by some number. When we do that, what happens is, okay, so look at this. So if we distribute this n inside the parentheses, we have n times A plus n times B plus n times C plus n times D. And then now the coefficients are NA and B, so forth. The equilibrium expression is just constant, products over the reactants raised to the powers of their coefficients, which now are NC, ND, NA, and NB. But you see the n is constant in all these, so we can pull the n out, and this is really just the concentration of C to the C, concentration of D to the D over concentration of A to the A, concentration of B to the B, whole thing raised to the nth power, which is just K to the nth power. So the upshot of that is that when we multiply the coefficients of an equilibrium reaction through by some number, we raise the original K to that power to get the new K, the power of what we multiply through by. So here's an example. We're given that the K, the equilibrium constant for this reaction here, A3 plus 3B in equilibrium with 3AB, is equal to 0.339. What is the value of the equilibrium constant for 9AB in equilibrium with 3A3 plus 9B? So guys, go ahead and figure that out, and when you get an answer, come on back. All right, welcome back. So the relationship between these two reactions, equations, is that to get the second one here, we've first reversed the first, and then we multiply it through by 3. So we're going to do both things. We're going to invert the original K, so 1 over 0.339 because we inverted it, and then because we multiplied through by 3, we raise that to the third power, and so we get a value of about 25.7 for the K for this reaction. Okay, pressures and the equilibrium constant. So we can write an equilibrium constant not only in terms of concentrations, molarities, but also in terms of pressures if we're dealing with gases. And so Kp, we call this, the sub P just stands for pressures. If these are all gases, then the equilibrium constant, the Kp for this, is equal to the pressure, again, products over reactants raised to the powers of their coefficients. Only now it's the partial pressures of the products raised to their powers over the partial pressures of the reactants raised to their powers. So this is a chemical reaction that's occurring between gases. They're all going to be in the same container, right? It ends up the relationship between Kp and K, which is in terms of concentrations, is this right here. And I'm going to show you why that is in just a minute, guys. But Kp, this is basically the bottom line here for you. Kp is equal to the K times RT to the delta N, where R is the gas constant. Remember from the gas chapter, 0.08206 liters atmospheres per Kelvin mole. T is the temperature, has to be in Kelvin. And delta N here, this is the change in the number of gaseous products and reactants. So if these are all gases, it's going to be the coefficient C plus the coefficient D, all the number of moles of gaseous products minus the number of moles of gaseous reactants, A plus B. These are for the gases only. So here's why that relationship is true. We're going to start out with the ideal gas law. So PV equals nRT. So we can rearrange this, divide through by V. So P for gas X, the pressure for gas X, is just going to be the number of moles of gas X, which is, whatever, divided by the volume times RT. Remember, these are all in the same container, so the volume's the same, and their temperature has to be the same because they're in the same container, right? So the pressure really depends only on how many moles, the partial pressure depends upon how many moles of that gas we have. But this over here, N over V, moles over liters, that's just the concentration or molarity of, X, whatever that is, which means that the partial pressure of gas X is equal to the molarity of gas X times RT. Now, if we take our Kp, and for each of these pressures, we substitute this expression right here. So for C, it would be the concentration of T, RT, D, RT, etc. We still have the coefficients as the exponents. We have the RT in common to all these, so we can pull this out. This is RT to the C plus D on top. This is RT to the A plus B on the bottom. Because this is the bottom, we can write this whole thing here as the concentrations raised to the power of their coefficients times RT to the C plus D minus A plus B, which is what we just saw, K, this is K, times RT to the delta N. This is delta N. So that's why that is true. But the bottom line is that the relationship that you guys are going to need to remember between K and Kp is this one right here in orange. So for example, same equation, right? Let's say this is supposed to be a gas here. Suppose that K is at 25 Celsius is 0.013. What's Kp? And also, what are K and Kp for this reaction? Notice it's related to this one. And K and Kp for this reaction. Let's do it one at a time, okay? So go ahead and work them out, guys, and when you get an answer, come on back. Welcome back. So let's do Kp for this original reaction first. So there's our equation. Kp equals K RT to the delta N. R is 0.08206 liters atmospheres per Kelvin mole. Temperature was 25 Celsius. Add 273.15 to it to get the temperature in Kelvin, 298 Kelvin. Now here, okay, delta N. So delta N is, there's the coefficient for ammonia, the product is 2, that's the only product, minus, so this is our C plus D is 2, minus A plus B is 1 plus 3 is 4. So 2 minus 4 is negative 2. Watch out for those signs. So that means our delta N is negative 2. Sometimes it's positive, sometimes it's negative, sometimes it's 0. So that means Kp is equal to the original K times RT to the negative 2. Which ends up being about 2.2 times 10 to the minus 5th. All right, so now we have Kp. Let's look at those two altered reactions. So the relationship between this equation here and this one here is that we've basically just multiplied through by a third. So 1/3, so 1, 2/3 there, which means that the new K is just going to be the original K to the 1/3 power, which ends up being about 0.24. And the Kp for this, K prime P, is just the original Kp to the 1/3 because we did the same, we write the Kp the same way. It's going to be the pressure of ammonia to the 2/3 of a pressure of nitrogen to the 1/3 pressure of hydrogen. So it's just the original Kp to the 1/3 power, which ends up being, okay, remember we got this number here on the previous screen for the Kp for this reaction here. So this Kp is just that to the 1/3 power, which is 0.028 or so. And the same thing for the other one. Here, what we've done is we've both reversed the reaction and multiplied through by 5/2. So that means that our K double prime, the primes aren't important, they're just to distinguish them. The K for this manipulated equation is just going to be the inverse of this K raised to the 5/2 power. So that's the same thing as K to the minus 5/2. So 0.013 to the minus 5/2, which ends up being 5.2 times 10 to the 4th. And likewise, we do the same thing for Kp. We know the Kp for this reaction, we calculated a couple screens back, and so Kp for this reaction is just going to be that Kp to the minus 5/2, which ends up being 4.5 times 10 to the 4th. Okay, heterogeneous equilibrium. This means an equilibrium reaction where everything is not in the same phase. So, for example, the decomposition of liquid water to make hydrogen gas and oxygen gas, if that's an equilibrium, then this is a heterogeneous equilibrium because we have liquid and gas. It could be solid, liquid, solid gas, etc. Well, the important thing about this to remember is that when you have a heterogeneous equilibrium, anything that's a solid or a liquid does not appear in the equilibrium expression. We do not write it. And the reason is this. So if we wrote the K, we'll call it K prime, just products of reactants raised to the powers of their coefficients. Well, it ends up, we could write this as and we do, write the K as being equal to this times the concentration of water squared. Now, because the concentration of water, liquid water, does not change, if you think about it, it makes a lot of sense, right? How many moles per liter do we have? Well, I mean, it ends up it's like 55 or something like that, but it doesn't really matter. It's a constant. Even if we cut that in half, we take half of that water away, we still have the same number of moles per liter because we took half the moles away and we took half the volume away. So it's the same molarity. That's a constant. Same thing for solid. And so that constant is actually incorporated into the equilibrium constant. And so our equilibrium constant is just going to include all this stuff in there. And so we write our equilibrium expression for heterogeneous equilibrium without anything that's in the solid or liquid phase. So for example, for this reaction, this equilibrium, we would write the equilibrium expression as just being the concentration of hydrogen times the concentration of oxygen. Actually, this is not squared. Actually, it is. Excuse me, that's here, and there's supposed to be a 2 here. All right, so now, however, for this reaction here, which looks really similar, the only difference being that the water is in the gaseous phase, the equilibrium expression is different. Now, we do include the concentration of water because it's not a solid or liquid, it's a gas, just like everything else. So, what are the equilibrium expressions? So here's another example for K and Kp for the following equilibrium. So I'm not asking for values, just the form. Write down, when I ask you to write down an equilibrium expression, it's just K equals and then something over something, or Kp equals something over something. So here we go. Guys, go ahead and write it down real quick and come back when you get an answer. Welcome back. So, because we have solids here, they do not appear. Only thing we have that's not a solid in this equilibrium is the reactant carbon dioxide. So we're going to write K is equal to 1 divided by, this has to be in the denominator, right, because it's a reactant. So we need the 1 up there, concentration of carbon dioxide. Now, Kp, we could write as 1 over the partial pressure of carbon dioxide, but its relationship to K, we would write, remember, K RT to the delta N. Well, delta N is 0 minus 1 is minus 1. So Kp would be equal to K RT to the minus 1. And that's all there is to it, guys.